And hello and welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your pre-calculus. I'm going to be your pre-calculus teacher today. Just a little bit about myself before we begin. Again, my name is Joey. If you're tuning in for the first time at OneClass, here at OneClass, what we do is we provide online lessons and live material, particularly for subjects such as secondary school math and for chemistry. And what we do is we stream every day from Monday to Sunday. So we have many teachers here at OneClass. What we're doing is we're preparing free material for you. If you're a student at home or your viewer at home or just watching, then you'll be able to kind of follow along. You can catch up or review if this is a new material, or you can get ahead if this is some new material that you might explore in a further math course as well. Here at OneClass, what we're doing is we're dedicated to learning, to virtual learning, and what that means is that we're learning from home because despite of the school closures right now throughout the country and throughout the international scene as well. So here at OneClass, what we're doing is we're supporting learners virtually through our group of teachers here. Again, my name is Joey. Just a little bit about me first before we begin. I'm currently a teacher candidate here at York University here in Toronto, and what we're doing is I'm currently almost certified to teach in a secondary school, so in the intermediate senior division, particularly in chemistry and in music. However, I would like to get my math teachable further down the road as well. So, without further ado, let's begin and let's review what we did last session. So, what we did for last session was we talked about this topic of end behaviors, and we talked about this topic of domain and range. And if we think back to what we did last lesson, we did a lot of problems where you were given a function. Specifically a power function. So again, when we talk about this topic of polynomial functions, when we talk about a rational expression, or sorry, a reciprocal function, we talked about something called a square root function, or a power function with the exponent that's between 0 and 1, so with a fraction. And we talked about the reciprocal of that, so a power function with the exponent that's between -1 and 0. And what we did was we looked at all of these four functions. We determined the following things. We did continuity. So that's the first lesson that we did in the beginning of pre-calculus. We did continuity. End behavior. So again, as x approaches infinity, what would y approach? And as x approaches -infinity, what would y approach? Or as a limit, as x approaches infinity, what would y go to? We reviewed x and y intercepts. We did periods of increase and decreasing. That was on one of our earlier lessons from before. We also we introduced you to this topic of domain or range. That was something that was very, very brand new for us. So again, domain is where the function exists along in the x-axis, and then range is where the range of the function in the y-axis. So that's what we did kind of last session. And today we're going to move on to average rate of change, and this is actually a very, very important topic because we've actually done this before. Average rate of changes, we've done this before. If you were currently enrolled in a physics class, average rate of change is something you constantly do, especially in kinematics, and that's something you're very, very familiar with already. However, if you haven't taken physics, average rate of change actually appears very much so in earlier math courses, such as in Algebra when we talked about concepts such as linear equations and slopes. That's very much what an average rate of change is. So let me just define average rate of change before we begin. And a lot of these problems are very, very much the same, which is awesome. So that's what we're going to focus on today. However, average rate of changes does help us with building our idea of what calculus or introductory calculus is. So this is actually a very important concept that we'll need to talk about in terms of rate of change. So let me define average rate of change here. Average rate of change. So what is average rate of change? Here, what we have I'm going to define it as rate of change over a specific interval, or specific or two specific x values, or I would say over a specific interval. And now you're like, okay, Joey, what's rate of change then? So again, rate of change over a specific interval. And when I say specific interval, it's let me write this in blue. It's usually two points, between 2 points. So this is between maybe I'm going to use interval notation. So it says x1 and comma x2. So 2 points on the graph, 2 points of something is between a specific interval. Usually it's 2 points, and most of the time it's 2 points. And okay, so now you're like, okay, what's the rate of change then? So let me define rate of change. So rate of change here is the rate or the speed, or you can say the difference in y value as in that specific interval. So I'm going to say here, instead of rate of change, I'm going to define this as in terms of math. So in terms of our kind of situation here, and I'll provide you with an example because this is a bit more abstract when I define this mathematically. But this is as between x1 and x2, so between 2 points, how between x1 and x2, that's literally 2 points, and I'm going to say between x1 and x2, I'm going to say that how y changes. So how y changes over that period, or how fast y changes. So how y changes, and if it's how fast or how slow, maybe might be the better term in this concept. So usually I define average rate of change, and usually the example I give in this case, because this is still very, very abstract, is something called a velocity time graph. And for you science people, you might know what I'm talking about here. So this is just an example. So for example, if I have something that's like, I have a graph here, and this is time, and my y-axis here is velocity. So this is velocity. And what, for example, maybe it goes something like this. So this is my velocity, right? So the average rate of change is, what is the average rate of change in this case? So when I do the average rate of change, I'm taking 2 points. So maybe let's say here is x1, and then this would be x2 or something like that. Or maybe I'll do x1 at 0. Maybe I'll take the first point here. This is x1, and then I'll do x2 over here. So I'm taking 2 points in this graph. I'm gonna do this in blue. And what I'm doing is I'm finding, maybe it's around here. What I'm doing is I'm finding the slope of this graph. So this is the rate of change, so the slope of this graph. So you can say here, you can define it as slope, slope of 2 points. And that's really what we're doing with our average rate of change. What we're doing is we're trying to find out what is the rate of change between x1 and x2. And how do we find the slope? We know this from linear algebra 1, right? We know m, or slope, equals, we know it's y2 minus y1 over x2 minus x1, right? So that's something we know, and this is the average rate of change. In a velocity time graph, what it is if I have my x-axis here is time, and my y-axis here is velocity. If I take the rate of change in this case, I would actually get, in this case, blue. And in this case, for an average rate of change of a velocity time graph, I would get here, what this slope means is my average acceleration. So average acceleration, and what that is it's how fast I'm moving. So velocity is like, again, in the SI unit for this is meters per second, right? And time here is in seconds, whereas average acceleration here, it's meters per second squared. So this is actually really important in terms of physics, because when we talk about if I relate it to like forces or something, that's measured in meters per second squared. So that's what we're doing with that when we're talking about average rate of changes. So when we look at the function over the given interval, sometimes it's not defined as velocity or time. Sometimes it's defined just by the change in y over an x. So that's what we're going to do in today's worksheet. So let me go through number 1 with you. And number 1, what we can do is we can actually, because we're given the graph here, what we can do for number 1 is we can actually use this graph to solve our rate of change. So we can solve rate of changes 2 ways. If we are given a graph, what we can do is we can find the 2 points. So again, here, I'm not going to redraw the graph for you, just because if you want to solve it graphically, you need to be able to kind of edit this little the grid thing, which I can't do on a PDF file. But what we have here is we have f of x equals x squared plus x minus 1. And the interval is between, so again, these are two x values, right? This is between -2 and -7/4. Sorry, this is a square bracket. So how do we do this? We look at our x values here. Remember, this is x1 as x2, and what we're doing is with the graph, we are looking at where x1 is. So let's go x1. This is -2, so it's at this point here. This is x2, and -7/4 would be something over here, right? So again, we can't approximate using the graph, but what we're going to do, we're taking these 2 points and we're taking the slope at this line. So we're figuring out what the slope is at this line. So ideally, this will be negative, right? It's going downwards. This will have a negative slope. So remember, so you're going to recall that my if I want to figure out my slope, which is the average rate of change in this case, m equals y2 minus y1 over x2 minus x1, right? So we have, this is our slope formula. So we have x2 and x1, but how do we figure out y2 and y1? Well, how do we figure that out? We're going to have to actually use these x coordinates to plug into our f of x to solve for y2 and y1. So let's do x1 first, because why not? So x1 here is f at -2, right? So let's do it f at -2 equals, and then I'm evaluating this expression, right? It's more so, at the function -2, what will be my y value? So I'm setting x to -2. So it'd be -2 squared plus, or no, this is -2, sorry, -2 minus 1, which will equal, I'm gonna take out my calculator, -2 squared is 4, -2 minus 1 is 1, right? So that's pretty quick. I'm actually surprised I did that in my head, which is awesome. 4 squared, -2 squared is 4, -2 is 2, 2 minus 1 is 2, 1. Okay, good. So now we have this. So now we have y, this is y1, right? This here is, this is red, this here is y1, right? F at -2, this is equals y1, because y1 is what we set x1 to, right? That's what we figured out. And let's do, obviously, y2. We're going to need to do that. So let's do f at, and this is -7/4 would be x2, right? So f of -7/4 equals, this is -7/4 squared minus 7/4 minus 1. And I can't do this in my head. There's no way. But I'm going to use my calculator in this case. So it's -7/4 squared minus 7/4 minus 1 would give me, this will give me 5/16. 5/16. And this will equal this is our y2, right? So this is f at -7/4. Here is our y2. So now what we have here is we can actually solve for our slope, right? We have x1 and y1, and we have x2 and y2. So we can actually plug into this equation and solve, right? So let's do that. So in this case, y2 is 5/16 minus y1, which is simply 1. So 5/16 minus 1. And then x2 is -7/4. And this is minus 2, right? Minus and then -2 in this case. So again, we're taking the x2, we're taking the further point, and we're subtracting it by the earlier point. So again, x2 in this case is this point here, x1 is this case, and the order very, very much matters in the rate of change. So make sure you get the order right. So I'm gonna plug this into my calculator. So this is 5/16. Sorry about that. So 5/16 minus 1, and then we have here -7/4 minus, and then -2. And we will get a value of, this is -11/4 will be our answer for this one. -11/4 is our average rate of change, or the slope of the graph at these 2 points. So this is average rate of change. And I'm going to throw another term at you, because instead of saying average rate of change, mathematically what we're doing is we're actually solving the slope of, this is the secant line. So this is a new term here. So I'm going to redraw the graph. I'm going to redraw the graph here. And then again, I'm just sketching, right? And this is a brief, that's a really bad parabola. This is a brief sketch of what this is. I'm taking 2 points, let's say this point, and then I'm taking the slope of this graph, right? So slope of this graph here, or sorry, the slope of this line here. This line is called a secant line, and what a secant line is, it's defined as a line that connects 2 points together, or in this case, I'm gonna actually Google the formal definition for you. But it's a curve. It's a curve that intersects at least 2 points. So a curve, or in this case, it's a line that intersects 2 points, and this is the 2 points here, right? So this our secant line here is equal to, again, this is the slope, which is the average rate of change. Actually, this is just the average rate. Average rate of change is defined as a secant line. So why do we care about this? Why do we care about this math here? And the reason why we connect this to calculus later on is because in calculus we don't do rate of change. We don't do average rate of change. We still do rate of change, but we do something called an instantaneous rate of change. So what is an instantaneous rate of change? I'll briefly kind of go over that right now. I'll define what that is right now, but I'm not going to go into it because that's calculus in this case, because and this is simply just pre-calculus, right? So again, if I had a specific graph here, if I want to find the instantaneous rate of change in this case, I'm taking literally 1 point in the graph, and what I'm doing is I am taking the slope at this point in the graph. So again, this kind of line here, I want the slope of this graph. This line is not a secant line anymore. This is called a tangent. So tangent to the curve. This is something called, this line would be a tangent to this curve here, or this parabola here. And this tangent will let us define this is the instantaneous rate of change. Instantaneous rate of change, and that's really, really important in terms of calculus, because again, if this, for example, if this was a time, and even if this was a distance time graph here, the instantaneous rate of change at this point is my velocity at this point, and that's very, very powerful, because if I give you a time interval, for example, if you're traveling from I guess this time 0 and from to 60 minutes, and I want to know my speed at exactly 38 minutes, how would I do that? That's what instantaneous rate of change is. The speed at which that x value at that point would be my instantaneous rate of change. Again, the speed. If I'm given this is a distance time graph, but I'm solving for something else. I'm solving for the rate of change, so the speed, right? So it's very, very powerful, and this is what we're doing in calculus. This concept of instantaneous rate of change. And we won't actually go in depth into this until much later on when we talk about actually calculus and how do we solve this. But we're gonna do that's kind of the knowledge that we're heading towards, this idea of instantaneous rate of change in calculus. But for now, we'll just do an average rate of change, right? And this will help us prepare us for what calculus actually does here in this case, in terms of calculating instantaneous rate of change. So let's do number 2 here. I went on a little tangent, you could say, but it is important because a lot of you at home are asking why are we doing this? Why does this apply to me? That's why it applies. So I hope that kind of scaffolds the knowledge, and I hope that kind of puts things into perspective as to why we're doing this. So again, this is number 2. I have here this function f of x equals 1 over x minus 3. It's a reciprocal function, and the intervals are -2 and -3 over 2. So in this case, this will be, we're defining this as x1, and this will be our x2, right? Again, an interval notation. So how would we solve for this? I'll give you a minute to figure out how would we solve for the rate of change given this function at this given interval. So I'll give you a minute to do that. And let me throw up the slope formula for you. So again, here we have m equals. So how do we solve for this? How do we solve for this rate of change here? So how do we solve for this? So what we're doing is, again, we have x1, x2, but what we don't have is we don't have y2 and y1, right? So how do we figure those 2 points out? We're going to have to sub in these x points into our function to figure out this y2 and y1 points, right? So let's solve for y1 first. So y1, well, I'm going to use x1, obviously, right? So, I'm going to plug in f at -2. So this is f at -2 equals 1 over this -2 minus 3. What would that equal? This is 1 over plus minus, this is -5, right? 1 over -5. So that's our f1. That's going to be our f1 for, sorry, f at -2 is at, this will be here, will be our y1. And then we have this obviously solve for y2, right? So this is f at, this is -3 over 2. Now we're using our x2 point. We have 1 over, this is -3 over 2 minus 3. Plug that into my calculator. What would that equal? So we have 1 divided by, this is -3 over 2 minus 3. This is, I have here -2 over 9 is my answer. Let me double check that. Yeah, this is 1 over -2 over 9. It will be our y2. So this is y2. And then what we're doing is we're using this, we're going to solve for this slope, right? We're solving for this rate of change. So again, m here is y2 minus y1 over x2 minus x1. So y2 in this case would be -2 over 9 minus y1. Y1 here is negative 1 over 5. So the negatives do matter here, minus 1 over 5. And then x2 is -3 over 2, minus, and then minus 2. And then we're going to put that all into our calculator, and let's see what we get. So we have -2 over 9. This is minus 1 over 5, divided by, it's all divided by -3 over 2, minus, so this is minus 2. And we're going to get -2 over 45 will be our average rate of change for this problem. So -2 over 45 is the average rate of change between these two x intervals. So between -2 here and -3 over 2, the rate of change is -2 over 45. And we can actually use this graph to help us visualize or approximate this rate of change, right? So again, we have -2, which is over here, and then -3 over 2 is over here, right? So we know it's going to be negative slope, which this proves, right? So we just do a little check here. This is -2, 1 over 5. These 2 points, the slope of the line here is a negative slope. So let's do a couple more problems in this case, and in this kind of problem. Maybe let's do every other one, and then maybe I'll do this word problem, and we'll see how much time we have left, and maybe we'll move on to the next concept is transformations of functions. So maybe I'll move on to that after. But let's do every other one just so we don't get bogged down here. So this is number 3, and now we're not given graphs, right? We're just given our function here. Do they give you the same function? Oh, they do. So this is 3 over 13, and then they can just, oh, okay, that's how they did it. But for x minus 1 and for these functions, they don't give you. Yeah, they don't give you. Okay, that's fine. I was just curious. I didn't know if the graph they actually gave you the same graph, because they gave you the same function number 1. So this f of x equals x squared minus x minus 1, and this is between the intervals of 3 and 13 over 4. So again, take a couple moments, and if you're working through this problem at home, let me know through the chat as to how you're thinking about this problem, and let's approach this together. So again, this is f of x equals x squared minus x minus 1, and at the points 3 over 3, 3 over 14. So between these two intervals, so what is the average rate of change for this for between these two intervals? So again, what we have here is we have 2 points. We have 2 x points here. This is our x1, as here is our x2, right? So we have 2 points for our average rate of change, and now we have to figure out with the y1 and y2, right? And how do we figure that out? You gotta plug in the x values in, right? So again, let's evaluate f at 3 first. for this would be y1. So this would be 3 squared minus 3 minus 1. This would be 9 minus 3 minus 1, which is 5, right? 9 minus 3 minus 1 equals 5. And then we have here, let's evaluate this function at 13 over 4 for y2, right? So this is 13 over 4 would equal 13 over 4 squared minus 13 over 4 minus 1. And that would give me, I definitely cannot do this in my head. So this is 13 over 4 squared minus 13 over 4 minus 1. And we're going to get a pretty wacky value. You get 101 over 16, right? 101 over 16. And that will be my y2, right? So again, that's what the 0 is, y1. Sorry. 0 is y1, this is y2. Again, and now let's solve for our slope, right? So, sorry, you can't see this. I'm going to move this up here. I'll do this little slope in blue. So again, m equals y2 minus y1 over x2 minus x1. We have y2 is 101 over 16 minus 5 all over x2, which is 13 over 4 minus 3, right? And then we can plug this all into our calculator and get an answer. This is 101 over 16 minus 5 divided by 13 over 4 minus 3. And this will equal 21 over 4, which is our answer for number 3. 21 over 4 will be our answer in this case. It's the average rate of change between 3 and 13 over 4. So again, these are very, very abstract because what we're doing is we're not giving them a specific, we're not the function, like what does this mean in real time, right? So again, I like to visualize these as distance time graphs. So this is d at t at a, so I visualize this as this, like a distance time graph. So I can say something like distance. So at a specific time, what is the distance? So at d at t equals, and I would change these variables to t. So this is t squared minus t minus 1. So at what time, or between maybe 3 seconds and 13 over 4 seconds, what is the distance, or what is the average rate, not what is the distance, but what is the average rate of change between these two? Or what I'm saying is, how fast am I traveling between this point and this point is a better, it's easier to visualize that when you put it in terms of in a physics framework than a math framework, in my opinion, when we talk about average rate of changes. So again, that's just a little aside here. So we can, the word problem actually at the end will tell us to use rate of change. So maybe when we get to that, I'll show you what I mean when we talk about rate of change and how it applies in terms of a distance time graph or whatnot. So let's do number 5. So again, all of these things are applied in it could be applied in physics concept. It's applied in calculus and a lot of these other concepts as well. So hopefully it's something that's like something that's you've thought of before. So I'm not pulling things from thin air. So number 5 states this is f of x equals, this is 2x squared minus 2x minus 1, and the interval here is 1 over 1 and 3 over 2. So again, take a couple seconds, look at the problem. What do we do first? So again, what we're doing first is we're figuring out what's x1, x2, right? So again, this first number here is x1, second number here is x2. And what we're doing is we're finding the rate of change, right? So we have to figure out what y1 and y2 are, right? So in order for us to do that, let's figure out y1 first. We got to sub 1 into our function, right? So let's evaluate f at 1. This will equal 2. 2 times 1 squared minus 2 times 1 minus 1. 1 squared is just 1 times 2 is 2 minus 2 minus 1, which equals negative 1, right? So that's f at 1. And let's do, so this here is, again, our y1. And then we're going to do f at 3 over 2 to give us y2, right? So f at 3 over 2 is 2 times 3 over 2 squared minus 2 times 3 over 2 minus 1. Okay, I'm just going to cheat and use my calculator in this case. 2, 3 over 2, 2 times 3 over 2 squared minus 2 times 3 over 2 minus 1. And we get half here in this case. So again, how do we find our rate of change? Again, we know our slope function is m equals y2 minus 1 over x2 minus x1. Y2 in this case here is, this is y2, right? So y2 in this case here is half, minus, this is minus 1, all over x2 is 3 over 2, minus 1 is our x1. And we just plug that all into our calculator. So this is half minus 1, all over, this is 3 over 2, minus 1, and our answer here is 3. So 3 is our average rate of change between these two points. So we have one more problem before our word problem. So let's just do that problem, and we'll do these last two problems, and we'll move on from this topic, because I think we spent about half an hour on this, which is awesome. So let's do that quickly, and then we'll move on to the next topic of transformations, and we'll probably continue with that topic next lesson. So this is f of x equals this here. We have 1 over x plus 3, and our intervals is between -1 and -2 over 3. So again, how do we figure this out? What are we doing here? Again, we've been doing the exact same thing. Our 2 points here is x1 and x2, and what we're doing is we're figuring out y1 and y2, right? So we have to figure out what those 2 points are. So again, y1, we would sub an x1 into our function, right? So we would evaluate f at -1 would equal this 1 over -1 plus 3. In this case, it's just 1 over 2, right? -1 plus 3 equals 2. So f at -1 would give me half. This here is my y1. And then how do I figure out y2? Well, we have to figure out the function at -2 over 3, or x2, right? So this is simply 1 over 2 over 3 plus 3. And what this is 1 over 5 over 3, I believe, which is 3 over 5, if I'm not mistaken. I'm trying to change these into fractions and figure it out in my head. Exercise my mental math a little bit. Let me just double check that with my calculator. No, it's 3 over 11, sorry. That's my fault. Darn it. I think I multiplied actually here, and that's why I got it wrong. So this is 3 over 11. So we have 3 over 11 in this case, and then this here is our y2, right? So now we can do our slope calculation. We have here, we got m equals y2 minus y1 over x2 minus x1. We have here our y2 in this case is 3 over 11 minus half is our y1, all over this -2 over 3, our x2, minus x1, which is -1. So we have 3 over 11, so 3 over 11 minus half divided by, this is -2 over 3 minus 1, and we're going to get the answer is -15 over 22. That gives me -15 over 22. I don't know if this is correct. If you do scroll down in this case, you have answers here. So I'm just trying to figure out why doesn't this match. Let me give me a second actually. Let me redo my math. So this is the function, -1. So -1 plus 3 is 2, which is half here. So my y1 is correct. This is, oh, I plugged in +2 over 3 here. This is where I messed up here. So it's good to check your answers. So again, I'm not perfect, so sorry about that. I plugged in positive 2 over 3 instead of -2 over 3, which means this changes my answer here. So again, this is 1 divided by, this is -2 over 3. -2 over 3 plus 3 here, which is 3 over 7 is my new y2. So this is 3 over 7, which means this here is y2, so this changes here to 3 over 7, which means this changes my entire answer, which is, let's figure that out. So again, 3 over 7 minus half divided by, this is -2 over 3 minus 1, and I get -3 over 14, which is my correct answer. -3 over 14. So that's my correct answer for this average rate of change here. So again, sorry about that. I plugged in positive 2 over 3 in this case instead of -2 over 3, hence why I got a wrong answer here. So let's just word problem, and we will kind of wrap up average rate of change in this case. So this is number 9, right? I'm trying to figure it. Yeah, I'm gonna try to put it one screen for you. So number 9 states, we have here, the police have accused the driver of breaking the speed limit of 60 miles per hour. For Americans, we use miles per hour. In Ontario, we use kilometers. So I'm not very, I don't know what that is in kilometers, but I think it's like, I think we change it to 60 times 1.61. So I think that's the conversion. I don't know. I would have to Google that. Anyways, as proof, they provide 2 photographs. One photo shows the driver's car passing a toll booth at exactly 6 p.m. The second photo shows the driver's car passing another toll booth. I think this is supposed to say booth, not both. Toll booth, 31 miles down the highway at exactly 6:30 p.m. Does the photo evidence prove that the driver broke the speed limit during this time? So how do we calculate this? So again, we're using this concept of average rate of change, right? So we still use this concept of m equals y2 minus y1 all over x2 minus x1, right? Or we can actually rewrite this as, we can rewrite the change, or this delta y over delta x, right? The change in y, and if you're not familiar with this notation, this is just the change in y divided by change in x, right? And in this case, we're not given x or y. They're actually hidden in this case. What we're given instead is we're given speeds. We're given a speed of 60 miles per hour, and we're given times, and we're given a distance, right? So in this case, we would have to change our slope function to something called, this would be, the slope would be our speed, right? I'm trying to figure out if it hits 60 miles per hour. In this case, our slope here is our speed. So I'm going to call this v here. V is our speed, and I'll define this as our speed. This here is our speed. It's actually not velocity. If I put a vector sign, it's velocity, but don't worry about that. It's for you physics people out there. That's why I didn't choose to put the vector sign here, because speed is a scalar quantity. And the y2, we have y2 in this case. It's gonna be the change. If you know the speed equation, it's actually the change in distance over the change in time, right? So delta d over delta t, right? The change in distance and over the change in time. And so this is, again, this here is change in distance over the this is change in time. So again, d represents distance and t represents time. In this case, the units here, I'll put this in blue. The units here we're given here is this unit here is in hours, right? The time here is, it's given at 6 o'clock and at 6:30 p.m., right? So this is in hours, and this is in hours, and then time here, or sorry, distance here is miles, right? The second photo shows the driver car passing another toll booth 31 miles down the highway. So this would be miles. That's our units, and our speed obviously would be mph, right? Miles per hour. So our unit here is mph, miles per hour. So how do we solve for this? What are we solving for? We're solving for the speed, right? And if we're going to double check if it hits 60 or if it's over or below, right? So this is going to equal the change in distance. So how do you figure out change in distance? So let's do, let's read the question again. So it says here, one photo shows the driver passing a toll booth at exactly 6 p.m. The second photo shows the driver's car passing another toll booth 31 miles down the highway. So the change in distance in this case is 31, right? Because in this case we have they start from an arbitrary point. Let's say they start from point 0. So I'm going to use my interval notation again. They start from I'm going to say point 0, and they travel, another photo shows the driver's car passing another toll booth 31 miles down the highway. So the next point would be 31, right? So again, here, this is you can think of it as my, instead of x1, this is going to be my x, but this is going to be my d1, and this is my d2. So change in distance, again, it's just d2 minus d1, and change in time is t2 minus t1 here, right? So d2 minus d1 here is simply just 31 minus 0, right? That's good. So we figured that out. So what's t2 and t1 then? What's the change in time? How do we figure that out? So we figured that out in the question, right? It says here, one photo shows the driver's car passing a toll booth at exactly 6 p.m. So in this case, my T1 would be, my T1 here. Oh, sorry. Why did I download this image? T1 is at 6 p.m., right? At 6 p.m. And then here, T2, the next time, it says here, 31 miles down the road at exactly 6:30. So it's me 6:30 is my T2, right? 6:30 p.m. So again, T2 minus T1 here, you can convert this into hours. So I can say this here is time 0 hours, and then after half an hour passes, obviously it's half an hour, right? So 0.5 hours in this case. So I have 0.5 minus 0, right, in this case. And then, so that's T2 and T1. So I can simply do 31 divided by 0.5. 31 minus 0 is 31. 0.5 minus 0 is 0. 31 divided by half, I can simply rewrite that as 31 times 2, right, which is simply 62 miles per hour. And that's going to be our answer, our rate of change between, so this is our speed, average, so this is average speed this would be from 6 p.m. to 6:30 p.m. And all we have to do is we have to compare this value to the speed limit. The speed limit here is 60. We're traveling at 62. So unfortunately, yes, you are breaking the speed limit in this case. You are breaking the speed limit at some point. We don't know which point because we don't know the instantaneous speed or at which this guy is traveling at. But we do know that at some point in between 6 o'clock and 6:30, the person they should have been traveling. They would have been traveling at 62 miles per hour. So that's gonna be enough for them to issue your ticket, unfortunately. So in this case, there is evidence. So yes, there is evidence of driver breaking speed limit, and then we prove that. Because we prove that using this number. Again, 62 miles per hour is the average speed from 6 to 6:30. I'm going to clarify this at some point. This is between 6 p.m. to 6:30 p.m. So the police have enough evidence to kind of issue a ticket, unfortunately. So that's kind of our lesson on average rate of change. I hope you found that useful in terms of when we're looking at this kind of topic. We still have a little bit more time, so I want to move on to this next concept here, which is the transformations of graphs. So we're going to switch gears here, and we're going to talk about what a transformation of graphs are. So I'm going to give you a minute to kind of digest what we talked about before I start. I'm going to start writing some stuff here. But I'll give you a minute to digest what we learned in terms of average rate of change. So I'm going to start writing here. I'm not going to talk about for a bit, but just give me some time to kind of write this out. This is transformations of graphs. So when we talk about transformations of graph, what are we talking about in this case? So let's take something that's very familiar to you first before we talk about what transformations we're doing. Let's take, for example, actually, let me define transformations first. Transformation is if you think about the word transformation or transformer, like Optimus Prime or something, what we're doing is they are shifting. There's a change. They're shifting size or shifting some sort of value to make something new, right? So that's kind of the word transformation, right? So in this case, in mathematical terms, when we talk about transformations of graphs, we're talking about how the graph changes, and it could be change in different sizes. And it's just basically different sizes, and that's what we're doing with transformations of graphs. And what this allows us to do graphically is, if we look at the question 1 in this case, you can see here I have my blue graph first, which is I believe f of x, and g of x is the transformed graph, right? So you can see in this case there's kind of it shifts in points, and it's kind of reflected, right? You see a reflection of the original function along the other axis. So that's an example of what a transformation is. So I'm just right here defined as change in size or location of function. But again, all of our function properties still remain the same. Again, these two things are still parabolas, right? So again, it's just changing size and location, right? And how do we do that? So let's take, for example, let's use a quadratic function, because that's something we're used to that here. F of x equals x squared, right? That's something we're used to. We can graph this. We don't, or sketch this. Sorry, it looks something like this, right? This is a really bad graph. Actually, I think I'm going to use Desmos to help me out here. Desmos. And why I do that is I'm going to show you what transformations actually mean in this case. But I'll sketch this out, and I'll prove to you what we're doing with this graphing calculator, because there's a lot of behind the scenes work when we talk about transformation. So this here is the function f of x equals x squared, right? And I'm going to do that here just to make things a bit easier here. So we all know this function, right? This is a quadratic function. This is f of x equals x squared. So now we're about to talk about, okay, how do we change size and location of this function, or how do we change all this stuff? So the first type of transformation we can do is a shift, a vertical or horizontal shift. So I'm going to make a point here and say this is my title, transformations of graphs. So the first type of change, I'm going to say here, this is a vertical shift, or vertical / horizontal shift. So how do we shift something that's vertical or horizontal? So again, I took my function here. I'm using f of x equals x squared as my example here. So let's do how do you do vertical first? So vertical shift is, if I took my function here, f of x equals x squared. If I added or subtracted a value from this, so let's say I'm going to use d for this value, d, or plus or minus d. This is going to shift our graph up or down. So let's take it, for example, if f of x equals x squared plus 1. What I'm doing here, this plus 1 signifies that I have shifted or vertically shifted my graph, or shift upwards, or shift it's vertical, it's again up or down, right? So again, if it's positive, it's upwards, and if it's negative, it's downwards. Right? So I can say this graph here is shifted up by 1, right? And let's graph that. So x squared plus 1, as you can see here. All right, let me put this as a new function. This is x squared, and we have x squared plus 1. As you can see here, this parabola is shifted upwards by 1. This is my original function, x squared, and it shifts up by 1. As you can see, the vertex of this parabola is shifted by 1. So everything, the entire function moves up by 1. So this here is a vertical shift. We can also have a vertical shift downwards, right? With this, instead of plus 1, if I said minus 1, if plus 1 was up, obviously negative must come down, right? So again, the original function is this orange or red line here, and negative, x squared negative 1 would be, it's shifted downwards by 1 here. So again, this is the new vertex, right? So again, shift up by 1, or you can say negative 1 would be shift down. So what we can say about this is that we can say that if d is positive, so if plus d, then shift up. Shift up. If minus d, then shift down. So that's our first kind of shift here, or it's a vertical shift. This is a easy, probably one of the easiest transformations we can do with the graph. So it's a vertical shift. So what about a horizontal shift? How will we shift something that's horizontal? What if I want to go from left to right? So this is a horizontal shift. And again, I'm going to take the example. Let's use the example f of x equals. So instead of adding it to my function here, what I'm going to do is I'm going to create kind of a it's going to be instead of adding and subtracting from the entire function, I'm only changing the x here. So in this case, let's do this function here. So x plus 1 squared. So if I have this kind of function here, or sorry, not f of y. I'm going to do f at, this would be, let's call it c. And this would be still squared. So in our example, it would be f of x. Let's do x, let's say if c equals 1 in this case. And I have this function here, x plus 1 squared. So what it does to this function is it's going to, this x plus 1, here is actually very, very different from this x plus 1 here. The x plus 1 here was outside the function. This is in the function here. So what it does is, instead of shifting upwards and downwards, this is going to shift. And in this case, it's actually going to shift left by 1. And I'll prove that to you by going on Desmos. So let's do x. So x plus 1, and then I'm going to do the power of 2. And as you can see here, it shifted. My vertex became from 0, it is now from 0, 0, this point here is negative 1 and 0, right? So why does this shift left? I thought positive is right hand side, right? So in the x plane, or you can say in the horizontal axis in this case, the signs flip. So this is when it gets confusing. So I'm going to write this down for you real quick. And I'll show you why that happens. Why does it flip? So I have here, if this is c here, if this is plus c, then shift left, and then if this is minus c in the brackets, then it would be then shift right. And I'll show you if this was a x minus 1 squared, I'm going to prove to you that this shifts right. And if I click negative here, this is going to shift. This blue graph is now remember, this red here is always my original. The blue graph is shifted right by 1. So why does this happen? So if I give you an overall example of why that happens, it's because in the general equation of a function, it follows this kind of formula. F of x equals, and don't worry about the variables. We'll talk about the variables later on. But this is x here minus c plus, or actually there's a b here. Sorry, let me get more space. This is bx minus c plus d. So we've actually already talked about some of these ones. Plus d here, we know this is a vertical shift. Minus here is our horizontal shift. And we'll talk about a and b probably actually next session, because we won't have enough time. But why does this plus c shift towards the left? So if my c here was positive, let's do here, and actually I'll do this if, so let's do if c is positive. So if c is greater than 0, then it changes my function here, right? If c here is greater than 0, then I'm still left with f of x. A and b and x don't change, but I'm still getting negative c, right? If I plugged in a c here in this case, it does not change it. This negative here means that it's shifting left, right? This negative now denotes that it's shifting towards the left. So because that's negative, right? It's going, it's a negative x value, right? So this refers to this here, it's shifting towards the left. However, what if I did if if c here was negative? So if c here is negative, then I would have here, let me make some more space here. Then I would have f of x equals, this is a times bx minus c, right, plus d. right? Because I'm subbing in negative c in this here because c is negative. Or I could rewrite this as a times bx, simply pop two negatives, make a positive, right? Plus c plus g, right? And if it's plus g in this, if it's plus c in this case, I am shifting towards the right, right? This here refers to this point here. So we're shifting towards the right because I have a positive c value. So every time here, when we talk about, when we look at the function here, x plus 1 squared, what I'm doing in my head is I'm internally flipping this sign, this operation here. So x plus 1, think of it as like x minus 1, so it's shifting towards the left-hand side. So that's what I'm saying. That's what I'm saying here. So this might be a little bit confusing. This here is inspection more so. This here is an inspection. It's not actually what's happening mathematically, but when I see the function, if I see it's a positive c, then it's shifting left. If I see it's negative c, it's shifting right. But the math here behind this inspection is this here. This here supports what I'm inspecting or what I'm seeing in my function. So that's kind of a vertical shift and horizontal shift. I don't know if we're gonna get to structures and compression, but what I'm going to do is I'm actually going to, maybe for the last 5 minutes, I'm going to talk about reflections really quickly, because horizontal stretch and compression might take a little bit longer. So I'll do reflections first. So this is number 2, and this is reflection on x or y axis. So again, I have my function here. So first let's do reflection on x-axis. On x-axis. So again, I have here, if I look at activity number 1, this is a great example of reflecting along the x-axis, right? So again, this is here is my x-axis. This probably now shifts to here, right? So everything here, think of it, it flips to the x-axis. So again, it was positive here, and then it's going to, and this, you can think of this as the imaginary x-axis. It's going to flip downwards to the negative, right? So it's shifting, it's reflecting on the x-axis. And what does that mean? So if I had, again, for example, f of x equals x squared, if I throw a negative in front, so f of x equals negative x squared, this negative here denotes that this will reflect along, it's a reflection along the x-axis. So negative, so I'm going to say, and I'll prove it to you, give me a second. So I'm going to input here negative x squared, and as you can see, the original function here is red. It's flipped along. This here is the x-axis. Is now flipped along the x-axis. So if this here is negative, so let's say if negative sign, and this is right before the function. So a general statement for this is if this is negative f of x, then you get a reflection. Then reflect on x axis here. So that's my that's a reflection along the x-axis. And what about reflection along the y-axis? And we'll end off with this concept. I'll show you one example. So this is what about reflection on y-axis? So if, for example, again, if I had f of x equals x squared, what if I had here f of x equals negative x squared. So this is different. So if I inputted here and said this is negative x squared, or actually hold up, no, that's still the same. That's still the same function here. If I'm reflecting along, I want to reflect, actually, no, this is right. I'm reflecting along the x-axis here, or in this case, it's reflecting along the y-axis, right? So this is negative x squared. In this case, if you look here, it's exactly the same function. So in this case, if I'm reflecting along the y-axis, you can look at the y-axis here. I'm reflecting from the right side towards this left side. In this case of a parabola, it's exactly the same function, right? Because if you look at it in terms of algebraically, I have negative x times negative x, right? Which means two negatives make a positive, which is f of x squared. So algebraically, they're actually the same function. And graphically, they're also the same function. So it matches up, right? So in this case, reflection on the y-axis does not actually mean anything. But what if I took a function that's, I'll end off with this. What if I took a function that's, what if I did a line? So let's say, so to show you f of x, and then I have, want to reflect it along the the y-axis here in this case would be negative x, right? I'm flipping along the y-axis here would be negative x. So as you can see, the green line here is from quadrant 3 to quadrant 1. So this is the first quadrant, second quadrant, third quadrant, the third quadrant. So it's reflecting along here the x-axis. So as you can see, it's going from 3 to 1, and now it's going from 2 to 4. So that's a better example. The parabola here in this case actually gives you the same function. So I'm going to take a minute to review. What did we do today? So we did a lot of stuff today, which is great. So we ended off with, so let's go back to the beginning. We started off with this concept of average rate of change, right? So again, over a specific interval, how does y change in a specific interval, right? And we use the example of distance, right? We talked about how in a distance time graph, let me scroll down to distance. In a distance time graph, we have change in distance over change in time will give us our speed, right? So again, we're talking about the slope of the secant line. So again, a curve that intersects 2 points is a secant line. We're taking the slope of that line to figure out what the rate of change is. And we briefly talked about what instantaneous rate of change is. The slope of the tangent line where it's only hitting 1 point of the curve, and that's kind of an introduction to calculus. We talked about the average rate of change in the first half of our video. And then today, and then the second half, we talked about transformations. And we'll begin with transformations as for next lesson. But what we did here was we defined transformation as change in size or location of the function, and we use our example of x squared. We talked about vertical and horizontal shifts. So if x squared plus d would shift up, and then if I have x plus c and then squared in the outside brackets, it would shift left by 1. So again, up and down and left and right horizontal shifts. And we ended off this video with talking about reflection along the x-axis. So again, along the x-axis would be up and down, and then the y-axis would be left and right in this case. So those two are things we can do to transform our function. For next time, what we're going to do is I'm going to save this save this note here. And what we're going to do is we're going to talk about vertical and horizontal stretches and compressions. There's two types of transformations when we talk about stretch and compression. So stay tuned for that, and then we'll talk more about other functions in a later video. So as always, thank you for watching.